is Vincent, and today I'm going to give you a presentation about colors, not only on the product we are mentioning in the past few years, but also some of the application of the color. I think you are very familiar with the product line Kelly Chemical is providing. We have Organon, the metal complex dye, Plazo, the solvent dye for plastic, and also Naso, the nano pigment paints and chips, and finally the chromic, our color changing pigment. I'm going to share some of the problem we encounter, our vision for colorant in future. So the title of the meeting of the seminar today will be From Hue to Value, Colorant That Fits. So I'm not going to talk about the appearance of each pigment or dye. I would rather talk about energy saving, manpower saving, or some shooting issue. And I'm not going to simply talk about only the pigment we are providing. I'm going to share with you the light spectrum used in the color that solves the problem in our industry. Let's just start with a simple picture. So, because you can see on the picture that everyone has a different perception of the color of an apple. So the young boy in the picture say it's red, but the elderly say it's scarlet. But in the industry, we define color objectively by using spectrum. So assigning color names or codes that correspond to the spectral data. So to understand, I think we have to start with the light spectrum of each color, and that will help us to look into some problem like metamerism. So the next topic we are going to talk about will be the light spectrum and metamerism. So we can see that the light source is the first factor that influences the color we see. White color, or the visible light range, span wavelength from 400 nanometer to 700 nanometer. When discussing light source used for color evaluation, we refer to a standardized illuminant established by the International Commission on Illumination, the IEC. For example, for the A, it stands for the light source generated by tungsten lamp, while D65 is another common illuminant that does not exist naturally. It is a synthesized standard created from a series of calculations by collecting data of natural daylight from sunrise and sunset. The diagram shown here, you can see the energy distribution of different light sources, and it will affect the color we see in the slides afterwards. So this is the light spectrum of different color. But as you all know that when light shines across an object, it somehow absorbs and reflects light with different wavelengths. The reflect portion determines the color we see. For example, on the upper left-hand side, there will be the reflection of every wavelength of light will be 100%, so it will give you a color white. On the upper right-hand side, the object reflects mostly the blue wavelength, so it will give you a sky blue appearance. So different absorption and reflection pattern across the spectrum will create different shade colors. So on the right-hand side of this slide, it shows a series of spectrum of different colors. So this is obtained from an artist's website so these painters may not recognize the CI number of each pigment, but the painters will describe the color as, for example, lemon yellow, magenta, or cobalt blue. They choose these colors for their painting on the mixing behavior of each pigment or each color. So these are deeply connected to this, the choice of the color are deeply connected to the steepness and the broadness of the peak of each color. For example, for the lemon green, which is under the white and black, it has a steep and broad peak, which indicates a high brightness and excellence in mixing potential. So the spectrum of color is not only applicable to industrial use, it also can be applied to artistic application. So this is two common fruit, our daily common fruit. They have their distinct light spectrum. So every object has unique light spectrum. While I believe most of our customers do not discuss with us when they mix color or they choose color, so they may not be able to fully understand the potential of spectral data. So this will allow us to do more troubleshooting with the customer, and these related to one of the big issues for color mixing would be metamerism. It's a simple picture. It's easy to understand that. The situation in picture, I believe, is unlikely, but it will help us to illustrate the concept of metamerism. So two boys holding bags. When they are outdoor, the color is the same, purple, but when they are staying indoor, the color of the bags are different. So as a professional colorist, we can immediately recognize the two illuminants are different. So the one on the left will be similar to D65, but the one on the right-hand side will be A, the tungsten lamp. So this is used as an entry point to explain metamerism. There are different kinds of metamerism, mainly three kinds of metamerism, but today we are only going to focus on illuminant metamerism. When two materials match under one light source but not exactly the same. So for example, in the picture we explain why metamerism happens. For example, when you have a green color, it can be either mixing by blue, yellow, or white paint, but also it can be done by green, yellow, and white paint. So as the blue and green with different light spectrum, so the final product or the final paint, the color have their own distinct spectrum. So on the left-hand side, you can see this is the light spectrum of the color in the previous slide, the boy holding the purple bag. So you can see two samples, one is sample A and one is sample B. So they are both purple, but with different spectral data. Interestingly, you can see that on the upper right-hand side of the graph, it shows under the light source of B65, the two colors are the same. It is because it demonstrates the data on LAB value. So the LAB value of each color under light source B65 is the same, so the delta E is nearly zero. There won't be any color difference. But the LAB value actually are derived from a mathematical formulas representing area calculation. So for example, an area of 16, a rectangular area 16, can be either derived from a 4 times 4 cm square cm square square, or a 2 times 8 cm square rectangle. So they have the same resulting area, but actually their length and their width are different. So similarly, that the calculation is different. The LAB calculation for that color, sample A and sample B, is different in light source A, and that's why creating a significant delta E in the value, and that's why we see a huge color difference. But the main reason is that the light spectrum of two colors is different. So this will create a metamerism. So for example, if you're asking me that if we can fix the problem for these two bags, I would say it's nearly impossible, because the intersection of the two samples there are many intersections. So 1, 2, 3, 4, 5, around 4 to 5 intersections. So when you have a light spectrum of two products with more than two, I would just recommend the customer to start a new formulation instead of adjusting the existing formulation. So this is a simple graph or diagram that can present to you that metamerism, when metamerism will happen, and which one is the more ideal case and which one is curable. So for example, in case 1, 2 lines, if the black one is the sample your customer is making, and the red dot one is the new sample they are trying to copy the existing one. So if they are totally overlapped, this is the most ideal case. There won't be any metamerism and the color is totally matched under different light source. But in case 2, you can see that the shape of the curve is the same. It's the level of the curve is different. It's also able to be adjusted by adjusting the concentration while maintaining each component's ratio. It's doable. But in case 3, you can see that there are almost 4 intersections. So with more intersections, there may be more variable for the change in color adjustment. So in this case, we would rather tell the customer to start a new formulation instead of adjusting based on the existing one. And that's about the theoretical part of the light spectrum. I believe it's, for you, maybe it's very simple or even useless in the real application. But when you combine this light spectrum theory and the nanopigment technology and the curing method afterwards, so there will be a whole picture of the topic I'm going to present today. So before moving on, I would like to talk about the nanopigment technology that we are using at the moment. So when we nanolize the pigment, we want to achieve a high transparency, but while maintaining property of light fastener or heat resistant. How small should the particle be? And what's the ideal particle size that gives transparency with minimum energy consumption, a grinding process? This is actually related to the scattering intensity ratio. So when the scattering intensity ratio is below 10, we can consider the dispersion of the coating layer to be transparent. So different pigment actually will have different size for the process. For example, in our nano pigment product series Nano, so blue pigment, usually we grind to 130 to 140 nanometer to get the transparency. For green pigment, actually it's around 150 to 160 nanometer. And for the red pigment, it will be 160 to 170 nanometer. So, and further reduce in the size or particle size of the pigment will just bring little additional benefit and waste of energy. So we are not going to do further grinding on these kind of pigment. So the next one I can show you, this is the scanning electron microscope image for the pigment itself. There's a van der Waals force that will cause the particle naturally agglomerate. So in the conventional, this is all the agglomerated pigment particle. So you can see the pigment particle itself is not large. It's only 128, 180 nanometer, but when it agglomerates, it can be in micron size. In conventional paint manufacturing process, pigment are ground into micron level. So this one you can see the paint particle break down into smaller pieces, but it's still very large. So maybe 1 to 2 micron. It's still not in nano size. So in this level, manufacturer would add additive dispersion in the grinding process to ensure that these particles will not agglomerate again. For the product we are using right now, the nano pigment dispersion, we grind the pigment into nanoscale, so they have their additive dispersion that help the particle won't agglomerate again. So by looking at the SEM image, you can see a really uniform layer or dispersion, so to ensure a high transparency and uniformity in the coating layer. So why do we need to grind the pigment? So one, of course, is for the dispersion. Another one is for the transparency, but the most important thing is about the color strength. For example, in the conceptual idea is that when you fully disperse the pigment, the particle, the color strength of that particular color, for example, is 100%. So when we try to nanolyze the pigment, the color strength can reach 95%. But in the conventional paint manufacturing process where nanopigment is not required, the color strength is only around 70%. So when you try to nanolyze the pigment, actually it can give you a better color strength. So the consumption of the pigment in the system will be even lower. Before talking about our product series line, I would like to give you an example is that for printing ink, there are both solvent-based system and UV-based system. I would like to use a UV-based system as an example. So for the UV-based system, the choice of the UV lamp, UV curing lamp is very critical. For example, in traditional cases, we use mercury lamp, so it uses a high amount of energy when comparing to now to the modern LED lamp. So among these data, I will look into the energy efficiency of the LED lamp and the mercury lamp. So you can see that for the LED lamp, actually the energy efficiency is much higher than the mercury lamp. And the energy efficiency is the most important issue to most of the manufacturers. So LED lamps consume only 1/10 of the energy when comparing to mercury arc lamp. However, the LED lamp have high intensity and specific wavelength, but their penetration power is low. So the coating must be sufficiently transparent, or the coating has to be finely modified in order to maintain the shape of the dark color. So by adjusting the pigment content, we can increase the curing efficiency of specific LED wavelength. I use another diagram for the explanation is that block pattern is the wavelength energy distribution of mercury lamp. So you can see a broad distribution of energy intensity for mercury lamp under every wavelength. But for LED lamp, the intensity of each wavelength is really high. But as I say, the penetration power of the LED lamp is low. So if you don't have a transparent coating layer, it's not able to do an efficient curing process. But the rectangular shape I mentioned here, for example, I'm talking about 365, 395, and 405 are the wavelength we designed for our nanopigment dispersion for the curing process. So for Kelly, our capability is that we are able to customize nanopigment dispersion, allowing curing of LED wavelength of 365, 395, and 405. And I would say it's especially good for the dark color. So you know that for dark pigment, no matter it's dark blue pigment, it's easy to block the LED wavelength. But we are able to customize the nano dispersion that you won't see the color difference of the dispersion, but we can increase the curing efficiency of the LED wavelength at these three specific wavelengths. So these are the technology Kelly is owning at the moment, and we see our potential in the market. And also for the LED dispersion, nano pigment dispersion, we have different kind of monomer. The most common one would be HDDA, but we also are able to customize the nano pigment dispersion into PHEA and TMCHA. One example I can tell you that is the cell phone industry. So as there are some confidential information I'm not able to disclose, so I'm just going to describe verbally. So you know that for PCB board, there are different kind of color. You have green, you have blue, you have red, you have white, you have black. Nowadays, more and more cell phone manufacturers are using black PCB board for their internal part. One of the reasons is that black board have their own property, no matter it's the elegance or some heat dissipating power. But we all know that the black color is difficult for curing. So We are able to do the customization of the nano pigment paste in black that allowing the curing more efficient at the wavelength I described in my previous slide. And this is getting more and more popular in the market, especially for the blackboard. And this is the application I want to share with you. The customization power of Kelly is able to do not only in the traditional paint and coating industry, we are also able to do in the electronic industry. The final sharing case will be quite interesting. We get an issue from a resin manufacturer. So he told us that the color of the resin is yellow. It's a little bit yellow. Their customer is unwilling to take the resin from them because of the color. So the performance of the resin is, there's won't be problem, but the color of the resin is denied or rejected by the customer. So they come to us and ask if we are able to solve this problem. So I show you the result first. We are able to make the resin from red to colors where our resin manufacturer can sell this resin to their customer. So when we try to make it transparent, we also maintain, I would say, when we try to make it colorless, at the same time, we're also able to maintain the transparency of the resin. So we're doing some trick based on the spectrum of color. The resin now is yellow in color. So if you put blue nanopigment dispersion into the resin, the yellow resin, it will turn a little bit green. So this is what you can't do it because you are not able to adjust the color. But when you try to adjust the yellow into the red, into the green area, and then you add a little bit of pink to the resin. So the pink color will somehow, we call it eat the green color, so making the resin colorless. So you can see that the pink and green can get the color from each other. It's possible, but for the blue and yellow, it's not possible. It's because this diagram is actually inappropriate for the description of the axis on this diagram. Actually, it's an irregular shape. It's not really a circle. So when you put in a real case, the green is exactly opposite to the pink, but the blue is somehow near yellow. So you're not able to use blue to somehow eat the yellow color, but you can use the green to eat the pink or the pink to eat the green. So this is how nano pigment dispersion can work in real application other than paint and coating industry.